Hey everyone, I hope everyone's having a good day. We're going to take you through the entire electricity and magnetism or 6.1 notes. We're going to do this in three parts. We're going to break it up, but here are all the notes all together. I'll try to tell you when we're in part one, part two, and part three. So again, there's your assessment statements, charges, Coulomb's law, potential difference, all words we need to know. The first part of this, part one, is pretty easy, okay? A balloon attracts to wool. Balloons repel each other. This is because of, everybody together, good. We should know that that's because of charges, okay? If this balloon right here is attracted to this wool, then they must have opposite charges. If these two balloons repel each other, then they must have like charges. If we look at this, instinctively, wool produces a positive charge, while the balloon is said to have a negative charge. So that's exactly what we just talked about, and you can highlight that in your notes, and that's really important to know. The unit for charge is Coulomb, a big capital C, which is pretty easy to remember because when we're talking about charge, we're usually talking about something that starts with C. All right, this is a really, really important slide. I would star this slide. There's a lot of future test questions and homework questions and quiz questions and everything you could ever imagine coming from this. Though the unit is C, big capital C, the unit is Q. I like to think of it like a little small point or point charge, but inverted. There are two kinds of charges. They're positive and negative. All right, we've talked about how like charges repel and opposite charges attract. The fundamental charge of an electron is this number right here. And technically, it is the charge of both an electron and a proton, because if we remember from chemistry, while they are different sizes, they are opposite charges. So if it is a proton, it will be positive 1.6 times 10 to the negative 19th, or if it's an electron, it'll be negative 1.6 times 10 to the negative 19th coulombs. So, conservation of charge. Just like everything else we've ever talked about, charge cannot be created or destroyed. It can be transferred, it can be concentrated, but somewhere there has to be a conservation of charge. When we look at this, when we have a bunch of like charges and we're going to have repulsion, we are going to have more force. When things are neutral or not attracted, not doing anything, we say have no force. Most of the time there is no force because we have both sets of charges. This could also be true over here for more force if they were all positive. This is really the end of part one. You're going to do this simulation in class. So there is a link on Schoology. There's a little packet to fill out and you kind of go through there. So if you're ready to stop on part one, you can stop right now, and you can always come back and watch part two and three. All right, we're going to head on to part two, transfer of charges. These are all terms that we need to know throughout the entire part of chapter 6. We're going to learn them now and keep bringing them up. Conductors, okay? By definition, conductors must have contact, okay? So they really need to transfer electrons easily. So a great example of that is most metals. Wires, the actual metal components of the wires are great conductors. They allow electrons to move easily through them. The opposite is an insulator. An insulator does not allow it to transfer through smoothly. Glass, rubber, plastic. If you ever looked at a wire where the metal parts is, they're wrapped in rubber. Extension cords are wrapped in rubber. Everything around household outlets have plastic, rubber, stuff like that. All light bulbs have glass around them. A semiconductor is a conductor that allows them to move freely, but with a little bit of restriction. And superconductors are ones that are like perfect, absolute perfect conductors of electricity. Almost too good to where you could have short circuits or they would melt. Gold is a great example. Gold is one of the best conductors. Platinum, palladium, all unbelievable, but so good that they almost melt. They get so hot so quickly and transfer so much, we get a surge from that. All right, are there materials that electrons can easily move through? Yes, again, just really quick. These are the slides I show the freshmen, but conductors, yes. They allow to move easily. Electrons are loosely held. And again, as you notice there, you can see how those electrons are free to move. Okay, most metals, copper and silver, are the most common. Are there ones where they don't? Yes, insulators. All right, Electrons are tightly held, plastic, wood, rubber, most metals, most non-metals, excuse me. All right, and if you notice right there, you'll notice the electrons still do move a little bit, but they are not as free-flowing as they were in conductors. All right, so part two, at the end of part two, we are going to do what we call the Pith ball lab. This is a very important slide. You are going to want to look at this slide as we do the lab, okay? So we are going to be rubbing rabbit fur on an acrylic rod, all right? The rabbit fur is going to impart, the rabbit fur is going to impart positive, or suck the is going to take the positive charge off of the rod, leaving the rod to be electronegative, okay? Now, a pith ball is a neutrally charged thing, and a pith ball is just a fancy thing for this right here, and it literally looks like a styrofoam ball hanging on a rope. Notice as this negative charge comes towards it, and we touch the pith ball, it becomes charged negatively. You'll see that the ball initially will come and touch this rod, and then it will then repel the pith ball, almost like a Harry Potter type situation. For example, if we look at this little video out here really quick, we'll kind of suck out here, we'll go over here. I'm not going to listen to the volume, it's really staticky. But this guy charges this up, and I'll be doing this in class, but you'll notice the charge right there. Initially, it kind of repels away, all right? He grounds it, which means he lets it touch his skin, allowing it to go through his skin and kind of balance out again. She's got a little wobble to her. He's going to bring the rod up here close again. Initially, it's going to attract to this rod. He's going to go really slow so it doesn't just suck right up to it. You'll notice, look, feel that attraction right there. He's going to let it touch, and now notice as it shot away. Okay, we're going to go back and watch that one more time. He's going to bring it really close. It's going to come. It's going to give it a little kiss, and then it's going to shoot away because now it has imparted a negative charge through conduction. All right, and then he kind of does his little Harry Potter thing here. You guys are all going to do that. It does not want to go anywhere near that rod anymore because of conduction. All right, we'll come back out here. We'll go back. Oh, of course. Perfect. We'll go back to the slideshow. All right. These steps right here are basically what we are going to do in lab as well. But conduction, and the opposite is induction, okay? Where conduction requires contact, induction can be performed by just bringing something close to it. So for example, if you notice, the pith ball here has both charges. As the negative rod approaches, it is drawn over. If you notice right here, this is really important. Inside the pith ball, as this negative rod is coming towards it, it's like it summons or brings all the positives to it, and all the negatives kind of go the other way, get repelled with inside of it. There's this term of grounding. So as we kind of attract our positives over here, we can ground or kind of allow a path for the negatives to come suck out of here. Now, when we literally mean ground, we literally mean like a wire or something that literally goes into the ground, all right? We say it donates it, or if it gives it up. And then as you pull the rod away, what was left over is all the positive charges. So we are going to be doing conduction and induction in lab. Right, here's a nice little thing of induction, a little bit more zoomed in, a little easier to see. Again, you have your normal one. As you bring it closer, you'll notice both charges exist. Remember, this has already been charged by something, probably rabbit fur, something like that. We literally can touch this end with our finger and allow those negative charges to roll out. We now move away. Notice the electrons didn't disappear. They're not dead. They are in the ground. But then the ball becomes overly charged positive. Now, the opposite could be true. If we would have charged this with something that made these positives, then everything would be opposite. Then we would then send the positives into the ground and keep the negatives in there. Again, induction, no contact, no contact. All right, the other way we're going to do this is with an electroscope. All right, with an electroscope like this, again, now notice I made the rod positively charged, which I'll show you how we do that. Electrons become attracted and flow up. So now both of this rod, electroscopes, which I'm going to show you a real life one here in a second, has all the charges on them. But as we bring that positive charge, notice the negative form at the top and the positive kind of gather at the bottom. And as that happens, you're going to see deflection around here. So again, let's just go out really quick here. I'll show you this little video real quick. Again, if you're in class, you don't really have to watch these and you'll see this. Again, not the best video, but enough that we can do what we need to do. All right, that serves as basically our end to part 2. We're going to do the Pith ball lab at that time. And basically, we need to make sure we're ready to go at that time. Again, you'll really get to see it. This is what we're going to use in class, not as open as what he had. We have ours in a glass jar, an Erlenmeyer flask, if you will. Again, glass being a great insulator and all those things. So, hope you have fun in lab. And this is the end of part 2. If you're going to stay on and watch part 3, just hang on a few seconds. All right, part 3. So now we've done the basics. We've done a little bit of the physicalness of it. And now we're going to learn a little bit of the math behind it. So electric fields. All right, now what does this look like? To me, this looks like a planet. You have a big old planet right here, and you've got 2 other little orbs. Remember, Newton didn't know this, but Newtonian physics actually kind of holds true with the same thing as atoms. He had no idea of this. But what he said is that with all these masses we're attracted. Well, remember, an electron and a proton are just small masses, and an atom's just a bigger mass, like a bigger planet. If you remember from gravitational field strength, okay, we remember that our equation is F equals big G M1 M2 over R squared. Okay, M1 M2 over R squared. All right, and if we remember big G, okay, 6.67 times 10 to the negative 11. All right, we've done all that. And we did all this if we were in a little spaceship and everything. Well, guess what, guys and gals? Electrical field force is very similar. The equation looks almost similar. K is like big G. It's different, but it's very much like that. Instead of masses, we talk about charges. So that's Q1 and Q2 over R squared, again with radius. K is a different constant. K is actually easier to remember. 9 times 9. Okay, 9 times 10 to the 9th. All right. Again, notice with masses, we're dealing with charges. Everything that was masses are charges now. Everything that was masses is charges. Again, real quick refresher. Field lines, positive go outward, negative go inward. If you're a positive person, you tend to radiate outward. If you're negative, everything feels like it's in on you. Remember, the number of lines also reflects the strength. Again, we've kind of always done this. Again, close to the sphere, things leave at right angles. If we look at the Earth, where we have dipoles, where we have a positive and negative pole, you notice as they come in, I don't need to label this, but you should know if they're coming in, this is the negative pole. If they're coming out, this is the positive pole. And remember, when we get close to the Earth, just like we talked about with gravity, this is the opposite of gravity. Remember in class, we all pointed down when we talked about gravity, but everything looks uniform or a planar front. This would be positive, and we should not even have to draw these. If we were moving this direction, we should know we're leaving a positive and we're going towards a negative. All right, real quick check right here, okay? You should be able to just look and say, oh, these lines aren't joining. These are positive. These aren't joining. Well, these ones at the bottom are joining, so we have opposite charges. These would be similar charges. All right, real quick check. All right, take a quick second and look at these charges. So let's just do A really quick together. Is A positive or negative? Well, if we look at the field lines, they're all radiating outward, and a positive person does that, so that would be a positive charge. Let's pause this video for a couple seconds, and you guess the rest. So pause the video, take a guess, and we'll be right back. All right, hopefully you tried that. Let's try B. What do you think? They're coming inwards? Negative. All right, C, positive. Okay, D is negative. E, negative. F is positive. G, positive. H, positive. And I, no, positive. There you go. Hopefully you got those all right. Again, it's literally looking at the direction lines. Outward, positive. Inward, negative. Now, what about strength? That relates to the number of lines. So you don't really have to count them all, but you could be able to see. So let's look at the first one real quick. We're ranking, and remember, this is that greater than symbol. I always like to think of it as Pac-Man, or an alligator eats the bigger one. There's all the teeth. So which one has a bigger strength? A has more lines than B. So we would say A is greater than B. All right, go ahead and pause this video again. See if you can get the other ones. We'll be right back. All right, coming over here to C and D. It should be pretty obvious. Now, real quick bonus question. What's C? C is negative. D is positive. But that's not what's being asked. So which one is greater? Again, you could go less than, but I like to do the greater one first. D is greater than C. All right, coming down to the bottom. Real quick bonus, what are all those? Yeah, they're all positive. But which one's the greatest? F. All right, then the next one would be E, and then the other one would be in the last, or weakest would be G. Looking at the last one, real quick bonus, positive, negative, negative. Hopefully you can see that I is the greatest, then H, and then J. All right, so remember, inward, outward, positive or negative, strength relates to the number of field lines. Okay, so everything we've talked about is right here. Here's our magical equation, F equals K, Q1, Q2 over R squared. There's our constant. There's our units. There you go. Everything basically the same as gravitation, but this is officially called Coulomb's law. Coulomb's law. Again, we've already just talked about that. They are basically the same. Everything's right there. These are definitely things that we need to not memorize, but be able to look up. So I've consolidated them here. Sometimes we'll need to know the masses, but most of the time we need to know the charges as our Q1, Q2s. All right, here is an example. All right, worked examples. If a 5, and remember, this is micro Coulomb. Remember from the very beginning of the year, micro is times 10 to the negative 6. Nano is times 10 to the negative 9. So this is also micro. So this is actually 5 times 10 to the negative 6, and this is 10 times 10 to the negative 6. Okay? All right, so we have a 5 microcoulomb point charge is in place 20 centimeters from a 10 microcoulomb point charge. Well, are we ever allowed to be in centimeters? No. To move from centimeters to meters, we divide by 100. So that is 0.2 meters. Just change it right now. Calculate the force experienced by the 5 microcoulomb charge. All right, well, the only equation that we know for the force of any of these charges is force equals K, Q1, Q2, over R squared. Now, we might not use all of that, but that's what it is. And also remember, K is 9 times 10 to the 9th, and that's just located a couple back. What would our R be? Well, our R would be that 0.2. Okay, and remember, we are going to square that bad boy. All right, now, are we going to use both charges? Or if it just says how much is experienced by the 5 microcoulomb? Well, if we click over here, we can see we are going to use both charges because they are experiencing each other. So your Q1, your Q2, there's your radius. We substitute it in, wham, bam, there is our force, which is a very reasonable force. K is a very large number. K, 9 times 10 to the 9th, because we were dealing with such small things. Just like G was a super small number because we were dealing with such bigger things. All right. What is the force on the 10 microcoulomb charge? Well, we could do all this math, but if you really think about it, Newton's third law says for every action, there's an equal and opposite reaction. Well, I mean, the only thing that would ever change if you forgot is you would just flip these numbers, but mathematically, they're going to be the absolute same number. So this answer is this answer here. All right. If you remember from class, here we go. This is almost the exact same problem. Okay, what is the field strength between the charges from 10 centimeters from A? So again, if we think of planet A and planet B, they both are 10 microcoulombs. So remember, that's 10 times 10 to the negative 6, both of them. But we're pretending we're on this little mass right here. All right, so how do we do this again? Well, again, the only equation we have is F equals K Q1 Q2 over R squared. Now, we're looking for this imaginary chart, like if we were right there. So we have to think, I'm getting pulled this way, and I'm getting pulled this way. So when we do this math, look, remember, 10 centimeters converts to 0.1 meters. This is 20 centimeters, 0.2 meters. So if you notice, from planet A, we're doing that equation. Remember, we are leaving off the other one because we're worried about this. We don't have a mass big enough to worry about, so we don't put the other Q. The other Q, Q2, is this dot right here, but it doesn't have a mass that we worry about, so we don't put 0 in. When we do that, we get this amount of force per coulomb. When we do it the other way, and maybe I should use a different color. If we use this side to go over here, we're doing exactly the same thing right here, except now we're getting a little less of coulombic charge, which makes sense because the radius is farther. It shouldn't experience a larger charge. But then we have to get our final answer. And remember, it always comes down to, are we going to add these or are we going to subtract these numbers? Are we going to add them or are we going to subtract them? Take a guess. Did you say subtract? I hope you did because they are being pulled in opposite directions. All right? So again, you always take the largest minus the lowest and you get the resultant charge. Remember, if this point charge, where I'm putting the big blue dot, was maybe over here or over here, and both charges were pulling in the same direction, then we would add those charges. So the answer was we were going to subtract because we're pulling in opposite directions. This is the end of part 3. Remember, we did the basics. We did a simulation. That was part 1. Pith Ball Lab, part 2. And then finally, at the end of part 3, we're going to do these practice problems, which I don't know if you can guess, but you better believe that we're using K Q1 Q2 over R squared. Again, I know that seems like a lot because I am breaking it into 3 chunks, but hopefully you've watched it in parts and not all the way. We will see. And again, remember, be safe out there and have a great time. And remember, Mr. Tima is out.